See Lindelof videos. Antiderivatives and indefinite integration. You know, there are only kind of two things happening in calculus. There's integration and there's derivatives. There's kind of slope and there's area. The antiderivatives, we get these things figured out, but differentiation, in my opinion, is a little bit easier because it's a little bit more concrete, I think. So let's just start with this supposition. Suppose that we're asked to find a function f. So we're going to find this function f. And when they ask you, they usually ask for the function f, capital F. So f is often called the parent function. And we're asked to find f whose derivative is 3x squared. So we're given this derivative, and we're said, well, what's the function? Where does it start from? So usually what we do is this, you guys, right? Usually what we do is this. We say, we have our function f of x, and we say f of x is equal to x squared plus 3x minus 7. And then what your professor is usually asking you to do is to say, hey, well, what's f prime at x? And you do this. You use the power rule here. Like, hey, this is 2x. You multiply this times this. You decrement the exponent by 1, right? And you do the same thing here, and then you get this derivative. Now what we're doing is we're starting here. We're going to use this as our start-off point. So, and in this case, we're told that our function is, our f of x is 3x squared. And we're looking for parent f. But what we're told about this f of x of ours is that this is the derivative of this. So we're going backwards. Instead of differentiating, we're starting at the derivative and we're working our way backwards. So we come up with this answer. You say, okay, I believe that the answer is f of x is equal to x cubed. Say, okay, well, I think that works also. That works well. How would we find that out? Well, if f prime at x is equal to this, then we know we have our winner. So we say, okay, if I take, to prove this, I take the derivative of this and say, well, yeah, it gets me back to 3x squared. The only problem is, what if your function was x cubed plus 7, or 14, or, I don't know, pi, or 2/3? Then if you took the derivative, what would the derivative of this constant be? This constant would be, the derivative of the constant would be 0. So it's hard to find our way back. So all we can do is say this. We can say this with some certainty. We can say that f of x, the f of x that we're looking for, the antiderivative of this f of x is equal to x cubed plus c. What would the proof of that be? Well, the proof of that would be that what would f prime at x have to be? Well, f prime at x would have to be this. And it is, isn't it? 3x squared plus the derivative of any constant is 0. The last thing I want to tell you about this before I let you go on this is, it's really important to keep in mind, is that what we get here is we get a family of curves. We have all these functions that are parallel in this very weird way that satisfy, it's called the general solution. So please keep that in mind. So let's try another question. Let's try this one really quick. So we say, find G where G prime at x is equal to 2x. So hopefully you see this and you're like, okay, I can see what happened here, right? This is the derivative, so I'm going to work my way backwards. There was a 2 that was brought down to here, wasn't there? So you say, okay, well then g of x must have been x squared plus c. Why is that true? Because if this is the function and this is its derivative, then that's true, isn't it? 2x is the derivative of this function g, right? So, okay, you guys, this is important stuff. It's not super difficult. I mean, it gets to be a pain in the neck. And I hope you watched the really short videos I did on basic rules of integration, because there's just things you have to memorize. But as we work our way through this, this gets really interesting, and it gets much more reasonable. So thanks for hanging in there with me. I hope I answered some questions. If you have any comments, let me know. And if you haven't already subscribed, please do. Thanks.